All right, this section 8.5 about dot product. So definition of dot product says V is has components A1, B1, and W has components A2, B2. Then the dot product V dot W is defined as V dot W equals A1 times A2 plus B1 times B2, which is the product of their first components plus the product of their second components. All right, I'll let you read the properties there. Let's look at a couple of these examples. So let's do number one, V dot W. So V dot W then is going to be A1 times A2 plus B1 times B2, which will be, I'm going to write here, that will equal negative 2 times negative 3 plus 6 times negative 7. Right, that'll be 6 minus 42, and that'll be negative 36. Okay, and let's try number 3, V dot V. So that'll be the first component of V is negative 2, and the first component of V is negative 2, right? So it'll be negative 2 times negative 2 plus 6 times 6. That'll be 4 plus 36, and that's 40. Okay, that's it. That's a dot product and the other dot product. All right, let's go on to part 2. So part 2, I'm not going to do any of the examples. I just want to point out certain things about what we're going to see. So if theta is the angle between two non-zero vectors, V and W, then cosine theta is the dot product V dot W over the product of their magnitudes. Yeah. Notice we can rewrite. Let's look at this. So theta is cosine inverse of that, right? But notice we can write cosine theta equals V dot W over magnitude of V magnitude of W as, if we multiply by magnitude of V magnitude of W, we could write this as V dot W, right? The dot product equals magnitude of V times magnitude of W times cosine theta. Okay, it's just a different way of writing that equation. Yeah, and so notice you can find the dot product if you know their magnitudes and the angle between them, or you can find the angle between them if you know their dot products and their magnitudes. All right, so I'm going to leave letter C to do in class. We're going to find the angle between the two vectors that we're given. All right, one other thing to know is two vectors V and W are orthogonal if and only if V dot W equals 0. So if their dot product is 0, then they're orthogonal, or if they're orthogonal, their dot product is 0. Orthogonal just means that they act at 90 degrees from each other. That means the angle between them is 90 degrees, is what it means. Okay, that's what orthogonal means. All right, let's go on to the next page, decomposing vectors into two orthogonal vectors. So if V and W are two non-zero vectors, then the vector projection of V onto W is given by projection of V onto W equals the dot product over the magnitude of W squared times the vector W. Notice that this is V onto W. And then we'll draw a little picture just to show what does that look like. All right, to decompose V into vectors V1 and V2 parallel to W and orthogonal to W respectively, V1 will be the projection of V onto W, and then V2 will be V minus V1. Okay, all right, so let's do the first part, find the projection of V onto W. So this will be dot product of V and W, right, V dot W, over magnitude of W squared times the vector W. All right, so V dot W is going to be negative 14 plus 18. Negative 14 plus 18. All right, so V dot W is negative 14 plus 18, and that'll be 4. All right, so this will be then, let's write the magnitude of W also. So magnitude of W is negative square root of negative 2 squared plus negative 6 squared. That's a square root of 36 as 40, and that'll be 2 square root of 10. Yeah. Okay. So we have what we need. So V dot W is going to be 4 over. So the square root of so the magnitude if we square it is 40. right? We don't need to know that it's 2 square root of 10 times the vector w, which is negative 2 comma negative 6. Yeah. All right. So this is 1/10, right? So this is then negative 2 over 10, right? This 4 over 40 is just 1/10. So this is negative 2 over 10, comma negative 6 over 10, and then we reduce. We get negative 1/5. I'm sorry, and negative 3/5. That's our projection of V onto W. Yeah. All right, now, what is the projection of V onto W? What does it refer to really? Well, if we look at let's draw vector V and W. So I'm going to draw them on a coordinate plane, right? So V is 7, negative 3. 1, 2, 3, 4, 5, 6, 7, negative 3. That's a terminal point right there. So V is that way. W is negative 2, negative 6. About that way. Okay. And the projection of V onto W, this is V and this is W, is like putting or shining rays perpendicular to W across V and looking at the shadow. And so if we were to look at rays, I'm going to move this, circle this around just so I can draw it easier. If we look at rays perpendicular to W, right? So the shadow of V would be right here along, right, vector W. Yeah. If you look at the vector we found, negative 1/5, negative 3/5. That's it right there. Negative 1/5, negative 3/5. It's on W, and it's a shadow of V that's on W when we shine rays perpendicular to V, right? So all these rays make a 90-degree angle with V. Okay? Rays perpendicular to V, and they give us that shadow of V on W. That's why it's called a projection of V onto W. Okay? All right. Let's look at one last example. We're going to leave B for us to do in class. Find the vectors V1 and V2. And then number 2, we're going to leave all of that for class. And let's do the very last one. It says if D is a displacement vector of an object and moving the object in a straight line from points A to point B under a constant force F, then the work W done is computed by W is F dot D. I forgot to indicate F dot D is a real number, right? Because it's magnitude. I forgot what F dot D is. Oh, you're the product of the first components plus the product of the second components. That's a real number. All right. So it can be thought of that way. This is the work done. Or it can be thought of this way. Notice there's a projection of F onto D times the magnitude of D, and both of these are magnitudes. Or magnitude of F, magnitude of D cosine theta. Notice that's really the same thing as F dot D. Remember we talked about that? Where theta is between the angle between F and D. All right, so the example says a dog pulls a sled 200 feet across a yard on a horizontal path. She exerts a constant force of 25 pounds directed upward 15 degrees from the horizontal. Find the work done round to the nearest pound. Okay, so I'm going to draw a little diagram of how this is going. Notice I'm drawing the XY plane. So here's my distance displacement vector. It has a magnitude of 200 feet. And here's my my constant force of 25 pounds directed at 15 degrees. Yeah. So it has a magnitude of 25, I'm sorry, 25, and the angle here is 15 degrees. So I'm just going to either say that this is F dot D, or I'm going to write it this way, right? So magnitude of F magnitude of D cosine theta. So the work will be magnitude of F, comma, magnitude of D, cosine of the angle between them, which will be then 25 times 200 times the cosine of 15 degrees, and we're rounding to the nearest foot-pound, so it's 15 degrees cosine times 200 times 25, and I get 4830 about to the nearest foot-pound. So this is about 4830 foot-pounds. All right, and that'll be it for section 8.5.